So another application to integrals in a physical context is to find the moments and center of mass of an object. So basically, conceptually, what is the center of mass? I mean, if you have, a one-dimensional object and, like, say, two people at different places on, say, a seesaw, then the center mass is going to be that point where it's balanced. Okay, one of these people might weigh more than the other, and so this anchor has to be closer to them. Okay, but it's balanced, and there's no rotation. That's the one-dimensional example. Two-dimensional is, for example, if you have a pan that you want to balance with one finger, where should you put your finger at? Okay, and if it's a symmetric and uniform symmetric pan with uniform density, then you'll put it at the center, and all you'll need is one finger and it'll be balanced. So that's the concept of center of mass, and the moments are the sort of forces that act about that center of mass. Okay, so how much mass is hanging away from that center of mass. So here is the concrete definitions. Okay, so if you have a discrete case where, like this is just multiple people, you have a discrete case, you can count the number of people, then the total moment is going to be the mass of each of those individuals times the position. Okay, and you just sum those together. The total mass is just summing the mass there of each individual. And the center of mass is going to be the moment divided by the total mass. Okay, so there goes the moment, and you just divide it by the total mass. That's the discrete case. All of that was discrete. Now, what if it's continuous, right? What if it's, not about the people on the seesaw, but the seesaw itself? Maybe some parts of the seesaw are heavier than other parts, and so this rho, this linear density, varies with x, right? So a part of it that's higher density will weigh more. And so how do you work with that? Well, the total moment for a continuous case is x times rho x dx. Okay? And you could sort of see the similarities there. And if rho is constant and you just have a shape f of x there to get the shape of the density, then you'll have x times f of x there. And that's the special case where if rho of x is equal to rho f of x. Okay, so you could just factor out basically a constant density out of that shape of the density function. Okay, and for the total mass, likewise, you just you would compute it this way. It's rho of x times d of x times dx, and that'll give you the total mass. And the center of mass is going to be the moment divided by the total mass. For the two-dimensional case, again, we start with the discrete situation and then talk about the continuous one. The discrete situation, the moment about the y-axis, it's a little confusing, but it's actually the sum along, where you take each mass and multiply it by the x of that mass. And the moment about x is you take each mass and you multiply it by y. Okay? So that's how you define the moments for the two-dimensional case. And the center of mass is going to be the moment, for x is going to be the moment about y divided by the total mass. And you could see that the center of mass for the x coordinate of the center of mass does have the sum along the x values. The y coordinate of the center of mass has a sum along the y values. So you take the moment about x, which might confuse us, and it's actually you multiply the masses by y. Okay. And that's because if something's distributed along x, you could see that the sort of forces of gravity are acting in the y direction, and so that's where that sort of counterintuitive thinking comes from. You're looking at twisting when you're talking about moments. Okay, well, what happens in the continuous case? In the continuous case, we just will have the sort of analog formula where we take x times rho dx, okay, for my, and for mx we'll have that formula there, okay, because this is now a two-dimensional shape. So there's a lack of symmetry between my and mx there, okay. And again, this is because we're looking at center of mass only using integration over one variable, okay. The most appropriate place to talk about center of masses for two-dimensional objects is in Calc 3. There, you'll do double integrals, and that's the most appropriate place to address the issue of center of masses for two-dimensional objects. But here we're just taking a preliminary look, and so we'll just respect these formulas until we do the more general problems later in our learning. And so you'll get the x-coordinate of the center of mass is the moment about y divided by m, and much like the discrete case, and you end up with that formula. And the y-coordinate of the center of mass for a two-dimensional object, you'll take the moment about x, and you'll get that formula there. So let's look at a concrete example. Find the centroid. The centroid is the center of mass of the region bounded by the line y equals x and the parabola y equals x squared. So here's y equals x squared. It's the bottom curve, and y equals x is the straight line there. We just straightforward apply the formula, so we integrate x. The formula here has this x f of x. Well, we're not just integrating over one of these functions. We want the region bounded by those functions. And so that's why we're having a f of x minus g of x there, okay, for the actual shape. If it extended down all the way, then we would just have used x for the function, or if it was just y equals x squared, we would use x squared. But we only want that shape there. And so we subtract the two to get that region, subtract those two functions, and we end up with these integrals. We carry out the integrals and get 1/2 for y. And again, I'll remind you that it's not the same formula as for x, okay. We are integrating still, despite y, we're integrating over x, and so that's why that's happening, okay. We're not having this simple y formula there that we would use in a Calc 3 setting. So using that formula and just subtracting out the g of x squared, so you just sort of find the moment about x for one of the functions and subtract out the moment for the other one, if you want to think about it that way. Then plugging in these equations, plugging in the functions for into these equations, we'll get 2/5. And so our center of mass is 1/2 2/5.